Um, so let's see. So let's get started. So welcome back. So hope everyone dealt with the snow so well, and hopefully not so too many people actually showed up in the classroom, and then some missed out stuff. So if you showed up, did you have like a watch party here? Did someone put in their laptop and watch it on the big screen like a movie?
I suggested it, but everybody I suggested.
Oh, well, yeah. So, okay. Well, so I've heard that okay, so I'm probably exaggerating, but I've heard that watch parties for classes can be a lot of fun. You can talk in the background about the stupid stuff the instructor's doing and stuff with your peers without worrying about interrupting people. So if you didn't, get your opportunity for a watch party, I'm sure there'll be another snow day at some point in the future. So okay, and so hopefully, like the sound effects weren't so too weird. I came that video. So okay, so great. So today we're going to talk about variance, which is kind of a very important property of distributions. And also, I decided I needed to kind of catch up on a couple things about the geometric and the exponential distribution. We kind of covered these things already, but there are a couple of notes I felt still wanted to cover, so we're going to go back to those just a little bit. Okay. So before we get too far into the lecture, let's see. So we are in the variance part of the schedule. We're coming up on spring break, and we're getting close to switching to the statistics part of class. So far, if you've noticed, we've talked about things like expectation and variance, which are things that you might associate with statistics. We will revisit them. So far, we haven't thought of actually any data. We're just trying to model the world. And so hopefully that'll make more sense and exciting when we get into the statistics part of the class. Quiz, let's see, number 6 is today, so we'll stop the lecture a bit early. And homework 4 is out. I have some printouts of homework 4. I'm trying to estimate the right amount of printouts that people will take exactly all of them except one. And I've been under and overestimating so far. You can pick one of those up after class. The grades for homework 2 are out, and they were improved over homework 1, which is great. So I think that's good. The quiz grades are a little bit lower than I was hoping. Someone asked if the quizzes are getting harder. I don't know if the quizzes are actually getting harder, but I think I'm going to try and change a couple of things, and hopefully the scores will increase. My intention is not to make stuff easier. My intention is for all of you to get higher scores on all stuff. So we'll see how that goes. This will be like a partnership between me and you. Hopefully I want everyone to have a large score after, at the end of the semester. Also, if you look at the grades on Canvas, you can see the grades kind of coming in. You can start to get a pretty good sense of what your grade is in the class so far. There are a lot of people who are doing excellent in the class. That's great. Some people probably would like to be doing a little bit better in the class. If you feel like you aren't quite doing as well as you had hoped so far in the semester, a couple of it might be useful to, once when we talked about the start of the semester, which maybe seemed a little trivial at the beginning, but try and read the textbook before the lecture and then ask questions in the lecture. This is a good way to kind of see stuff twice. There's not a lot of length covered in the textbook, so you'll read like 3 or 4 pages. So it should be shouldn't take too long to kind of start pre-processing it. the other thing I, recommend going to help hours. We have help hours basically, so like every day of the week. And a lot of people come in right when the homeworks are due. The homeworks are stuff that I think is good practice for you to work through with the, and the help hours are a great source, but you don't have to just go to the help hours for the homeworks. You can go and ask about other stuff, or I'm available after class to answer questions. So, so those are some things to keep in mind. So, okay. Yeah, okay. Great. So, all right, let's get into the lecture. So let's start by just reviewing expectation, because we're going to need expectation to define variance. Okay, so the expectation is kind of a property of a distribution or of a random variable. You'd say, so often you have a random variable x, which is from some sort of distribution, and there's some parameter of that distribution. That could be like a Bernoulli distribution with parameter p, or exponential distribution with parameter lambda, right? Some distribution. And then you say expectation of this random variable x, right? That's a property of the distribution that the random variable is so from. Yes, okay, so let's see. So if you have a discrete random variable, so this is for discrete, then you have a discrete set of possible values that the random variable can take, and you sum over the probability that the random variable takes on that value times the actual value, right? These values are some discrete subset of the real values. They're often like the integers, or like the positive integers, or 0, 1. And it's defined in this way for continuous, the expectation for continuous random variables, we need to replace those with an integral instead of a sum. And then you have a from negative infinity up to positive infinity. And you again write a dA. And instead of the probability, you have a PDF of this random variable. And so you evaluate that, PDF, and you integrate instead. Okay, so it's just a review of expectation. And so for a lot of the distributions we talked about in the earlier few weeks of class, we can calculate that random variable, and it will depend on the parameters. So depending on what this choice of parameter is, will somehow influence the expectation. And you can typically look those up. In a few cases, they should be pretty simple to rederive, like in the case of like a Bernoulli random variable, right? You should know what the expectation of a Bernoulli random variable is, or a normal random variable, right? So for instance, a Bernoulli random variable with parameter p, right? So this is a binary random variable, it takes one of two choices. Then the expected value of x is going to be exactly equal to p, right? So this is where it can take 1 with probability p and 0 with probability 1 minus p. Okay, another example would be if x is a normal random variable with parameter mu and sigma squared, and the mu tells you the middle of this distribution, right? So there's it's kind of a bump. Mu is the middle, and then this standard deviation sigma is kind of the width of it, about halfway up. right? And so then in this case, the expectation of X is equal to exactly mu. It's the middle. Again, for a continuous random variable, the mean is the balancing point. So if I put the distribution on my finger, it should balance if I put my finger exactly on the mean. Otherwise, it's going to tip over one way or the other. Because that distribution is so symmetric, then it's the mean, the expected value is exactly in the middle so this parameter mu, right? And so the expected value is kind of, if I were to draw a bunch of random things and take the average, that's from that distribution, that's what the expected value captures, what I expect the average to be. Right. So, okay. Right. This review of expectation. And if you missed the lecture yesterday on Tuesday, you haven't seen it yet. So YouTube. Okay. Okay. So what we're talking about today, the topic of today is the variance of a distribution. Okay. And this will be kind of another property of a distribution. This is a property of a distribution or a random variable from a distribution. Okay, and this one explains generally how spread out so the distribution is. Okay, so the larger the variance, the more spread out this distribution. The smaller the variance, the less spread out, the more what's called concentrated the distribution is. All right, so and we'll, all right, so let me write down the actual definition. So if I have a random variable X, right, again, from a distribution, an abstract sort of distribution, then the variance of X, okay, so this is the variance, usually uppercase V, lowercase AR. Instead of just one big E, you write 3 letters now. It's a little bit more specialized. And this is defined with respect to the expected value. Okay, so you can define this through the expected value. Okay, and this is defined as, let me write this down. It's a little bit confusing to parse the first time you've seen this. Okay, so this is the definition of the variance. Okay, I've got 2 expected values in there, which is a little bit confusing. Okay, and so what's going on here? Okay, this is the expected value of X, and importantly, it's so this is a constant. Okay, that value E of X is it's a property of the distribution, and we assume the distribution is known. Okay, so E of X inside there is a constant, but this X is a random variable. Okay, so this is the random variable that the variance is taken over. Okay, so that part is variable, whereas even though I have this X inside the expectation that I've underlined in green, right? Even though I have that X in there, that's just a representation of a constant. Okay, so that is a fixed value. Okay, and so what I'm doing is I'm measuring the random variable with respect to the expected value. What's the difference from it? Okay, and I want to say, what's the difference in either direction? So what's mathematically convenient, it turns out, is instead of like an absolute value, is to square it. If I square it, it doesn't matter if it's to the left or to the right. If it's larger or it's greater, I'm measuring the distance, the squared distance. Okay? So it's the expected squared deviation from the mean. All right, so that's how you would like think about this. It's the I'm exactly interpreting the formula. The expected squared deviation a random variable takes from a distribution from the mean of the distribution. Okay. It is indeed a little bit weird that I'm talking about the squared quantity here. Okay. The squared quantity makes this a little bit weird to like talk about and discuss, because if my units, I'm measuring time, right? Let's say I have a continuous random variable like the exponential random variable. I'm talking about the time until something happens, right? The expected value is discussed in terms of time, right? And so in terms of, so seconds, right? If I measure the random variable in seconds, the expected value is also in seconds. The variance is in seconds squared, okay? That, if you're taking a class in like, so physics, you probably thought about seconds squared in some sense, right? It shows up in places, but it's kind of strange, right? So, so it's a little bit weird to think about and to discuss. So what is common to do, what is to talk about another kind of so property, which is the, so which is going to be the standard so deviation. Standard deviation. Okay, and sometimes this is written as sigma of x. So this is sigma of x, and this is the variance of x defined as above, and I take the square root. Okay, once I have the standard deviation, it's basically the same quantity. I know the variance is always so positive, so I can always take a square root and still get a real number. So that's basically the same thing. I haven't changed any amount of information here, but I've gotten it into units that are the same as the random variable I'm talking about. So if this was in seconds, standard deviation still measured in seconds, right? So if I have a, so for instance, remember we've talked about the normal distribution, and I'll come back to this just a little bit. This was mu, was some point in the middle, and then I wrote sigma as this parameter, which was roughly the about halfway up the distribution, the distance from the mean to the the boundary. I can draw sigma on here. Sigma is indeed the variance. So sigma is indeed the variance, but I can't really draw sigma squared, right? It doesn't make sense in this drawing because it doesn't have the x-axis is in the units of like seconds, but so I can't draw something in the units of seconds squared. That just isn't going to make sense in this drawing, right? So that's why it's convenient to have the standard deviation instead of the variance. Turns out the variance will be mathematically nicer to work with and talk about. It's defined directly as an expected value. The standard deviation is defined as the square root of an expected value, which is a little bit even stranger to kind of, so think about. So, okay. All right, so these are the kind of the two quantities that measure how spread out is the distribution. If I were to take the normal distribution and spread it further out, right, then that sigma parameter would get larger. And if it would be more narrow, then the sigma parameter would become smaller, right? So it's kind of measuring how spread out is the distribution. Okay. Let's do simple example. Variance, where we'll actually do some calculations of the Bernoulli random variable. Okay. Yeah. Question. Yeah, whereas, okay, you're thinking about statistics, first of all. I don't have a population yet. I don't have any data yet. I have a distribution. And where that shows up is in the expected value is kind of doing that. Remember, the expected value is kind of like a weighted average, right? We talked about this a little on Tuesday, where this term here, I can think of a weight, right? And if everything is equally likely, that is 1 over n different options, and I can factor that out, and then it just becomes an average, right? So the expectation is already an average, and because it's an expected value of some squared quantity, I've got kind of an average built into that. That's what the expectation is doing. It's saying, what is the average? If I were to pick a random point from the distribution, right, that black point down there, what's, but in general, if I pick any random point, what's the expected squared distance from the mean? Right, so this is the distance from the mean. This would be x. That'd be this distance there would be x minus mu, and I squared that, right? So there's some more probability of picking it, less probability of picking it further out, and that gives a larger value. More probability, the density is higher as I get closer to the mean, right? And on average, over all points x I pick, this is the average squared difference from the mean. That's what the variance is. And then this standard deviation is the square root of that. Great, so thanks. It's a good question. Okay. All right, any other questions on that? Well, okay, the normal distribution is this kind of nice case. It has 2 parameters, right? One parameter, the expected value of x for a normal distribution, is exactly the first parameter mu. And the variance of that distribution, remember, we would write a normal distribution as, right, so the normal distribution is parameterized by mu and sigma squared. That second parameter is the standard deviation squared, which is exactly the variance. Okay, so those parameters are kind of independent of each other. I can set one and vary the other, or kind of vary one, and I can choose any combination of those. And as long as the variance has to be positive, okay, but any combination of those values, and I can get a valid normal distribution, right? So one controls the variance, one controls the kind of the expected value. Okay. Yeah, so that was going to be, I think, my kind of third example to walk through, but we'll kind of, yeah. Okay, so let's start with the simpler one. We can easy to calculate things straightforward. Let's do a Bernoulli random variable, right? So I'm going to have x is from Bernoulli with parameter p. Remember, this is a binary random variable. It's 1 with probability p, 0 with probability 1 minus p. Okay? And so we want to calculate, let's review the expected value of x, because we'll want this in the calculation, right? So what is the expected value of x? Is p? Yeah, okay, good. We calculated that before. All right, that's important to know. Okay, and so now let's the variance. So the variance of x, right? We'll write this out. This is the expected value of x minus the expected value of x squared. Okay. But we have the expected value of x here. So we can write this as the expected value of x minus p squared. Okay, p is a constant that depends on the choice of the distribution. It's a property of the distribution. All right, so it's x minus p squared. Okay, and now we can calculate this expected value. Okay, we can write this as the sum over ai equals 0 or 1. Those are the two values it can take, right? Times the probability x is equal to ai times ai, right? And so this is equal to, there are two terms in the sum. The first one is the probability it takes is if it's 0. So the probability it takes 0 is 1 minus p. And ai in this case, ai is going to be x minus p squared. Okay, so the probability it takes on so that would be the expectation of x, right? But we're actually doing so we're taking the expectation of, let's say, y here, and y equals x minus, okay, so we'll say y equals x minus p squared, and x is in 0, 1. All right, so, okay, so it's the expectation of y of the values that, so ai can take on here, and it can take on a value depending on x. Okay, so if x is equal to 0, right, what is this term here if x is equal to 0? Yeah. Yeah, right. So it is, writing this out a little bit more detail, it's going to be 0 minus p squared, right? Which will be minus p squared, which is p squared, right? And the other term is the probability that x takes on 1 is p. And when x takes on 1, then y will take on the value of, what's y going to take on then? So 1 minus p squared, okay? All right, and so now I can, now I have everything written in terms of p, right? There aren't any more variables left. So now I just need to kind of, try and do the calculation. So I'm going to get 1 minus p times p squared plus p times 1 minus p squared. And so I can now factor out p times 1 minus p, right? So I can factor out p times 1 minus p times what was left. I have p plus 1 minus p. Okay, but it turns out 1 minus p plus 1 minus p, this is exactly equal to 1, right? So this is equal to p times 1 minus p. Multiplying by 1 doesn't do anything. Okay, so the variance, that's the answer. The variance of a Bernoulli random variable is p times 1 minus p. Okay, its expected value is p, its variance is p times 1 minus p. Yep. Yeah, so a sub I, okay, is great question, right? This a sub I is this term here and this term here. Those are the values that y can take on, right? This value y, that can take on the value 0 minus p squared or 1 minus p squared, right? Because x takes on 0 or 1. And when I plug x equals 0 into that expression in black underlined in red there, I get 0 minus p squared. That's the first thing I've highlighted here. If x takes on the value 1, then x minus p squared becomes 1 minus p squared. And that's the second thing, right? Okay, so when you have an expectation of a function, what you do is you look at the values that function can take on based, and that function will have parameters of maybe another random variable, and you pass in all the instances that can take on. Okay, and so this is an example. All right. Yeah. Here, yeah, that's a negative. That's a minus sign. That's 0 minus p. Yeah. So I'm worried by, yeah, is that okay? 0 minus p and 1 minus 0 minus p squared and 1 minus p squared. Those are the two values that y can take on. Y is the random variable that represents, so this is including the squared, this is the random variable y, right? And so I want the expectation of that random variable y, and I know the distribution on x, and so y is a function of x. So I look at all the values x can take on, I pass them through this transformation to get y, and I can do this calculation. Yeah. Well, so the way I've used AI here, it's the values that y can take. Right, so I'm looking at the probability y is equal to AI. The probability that y is equal to anything other than 0 minus p squared or 1 minus p squared is 0. Those are the only two values y can take. Right, x can take on 0 or 1, and y is a function of x. Yeah. Yes, that's right. Yeah, so when we said x, we assumed here x is a Bernoulli random variable. It's like a coin, a biased coin that lands on heads, success with probability p. So we're assuming we know the laws of like the weight ratio of the coin under some standard flip, right? And that it's a random process, right? So the probability is to model the world, and statistics is to model data observed from the world, right? Yeah. I'm multiplying by the value that y can take on, right? So I'm going to write, I can think of this is the expected value of y, right? Where I've, so if I've just replaced the expression in the red box by y, and then AI are the values y can take on, right? So I could write in here, the values it can take on turn out to be 0 minus p squared and 1 minus p squared. Those are the values it can take on when I'm looking at the expectation of y, right? Remember, I'm not doing the expectation of just x anymore. I did that. I did that earlier to get that the expectation of x was p. Now I want to get the variance of x, which is the expectation of x minus p squared, right? So this is a nonlinear transformation, so I can't use the linearity of expectation to factor stuff out. I have to work through these calculations. All right. Okay. Good. Okay. Let me do, instead of another distribution example, let me show you that the variance has another form, and we'll kind of see some of these properties again. I said that the variance of x is defined as the expected squared deviation from the expected value of x. When I wrote it, as I said, in the nonlinear order, I got the spacing wrong, but Okay, so I defined it this way, but there's another convenient definition which I'm going to derive now. And that derivation, I think, will also be kind of insightful about how this works and in the importance of this being a constant. Okay, so I'm going to derive another useful way of writing this down. That's a completely equivalent, just sometimes easier to calculate this other form. And I'm going to do it by doing the expanding that squared term inside the expected value, right? Through linearity of expectation, I can factor out constant multiples. And if I can do sums of things, I can factor that out. But a nonlinear thing, that's the squaring is nonlinear, right? So it doesn't follow linearity of expectation. I have to kind of do those operations inside the expectation, right? So I do this and I get x squared plus e of x squared, right? Minus the cross term, which is 2x times e of x. Right, so all I did is I took that x minus e of x and I squared this. I expanded this kind of square term, right? Okay. Now I can apply the linearity of expectation, right? I have things I'm adding together inside. I can factor those out. So I can write the expectation of x squared, right? So I can factor that out into the other terms. Yeah, now I have the expectation of x squared. But this, remember, this guy was a constant. And so if I square it, it's still a constant, right? The expectation of a constant, I just factor that out. And this is also expectation of x squared. Okay, so that's a constant, I just factor it out, right? And then here, I want, again, what can I factor out? I can factor out the constants here are the 2 and the e to the x. Okay, so I'm going to factor out 2 times e to the x. And what's left over is the expectation of x. This term is coming here. Okay, that step's a little confusing. But so that's also from, yeah, so from this, right, it's coming here to get that term where the red part, the parts I have underlined in red, those are constants, I just factor them out. Okay, now I can simplify this a little bit. All right, where can I, it's a little, maybe it's still a little confusing. I've got some squareds, I've got some e to the x's. What can I simplify here? If you're way ahead of me, don't jump all the way ahead. What's the simplest thing I can simplify? Yeah. Yeah, right, okay, I can group them together. I'll do this in 2 steps, right? So this first term comes down as before. And then I'm just going to bring the second term down. I will handle this one in the next step. Okay, and then this third term, I can write e to the x squared. Right, so they're e to the x times e to the x, that's e to the x squared, right? Those are both constants, yes. Yeah, so e to the expectation of x, right? Okay, so good. This is a great question, places where there's lots of easy to get confused. Remember the Bernoulli distribution. What was the expectation of x from a Bernoulli distribution? It was p, right? Okay, p is a constant defined by the definition of the distribution. P is, say, 0.6. It's a constant, right? What's the expectation of a constant? Expectation of 0.6. It's just 0.6. That's it. The expectation of 0.6 is 0.6, right? There's no variables. that's a quantity I can know ahead of time based on my modeling of the distribution. So so there are two expectations, but if you see two expectations, you can combine them together. Okay, so that's what happened. In this case, it was expectation squared. So it's like p squared. That's still a constant that's factored out. Yeah. Okay. Now, I can write this as the last two terms, as was suggested over there. They're both a constant plus or minus times e to the x squared. So I can combine these together. Right. So again, I bring down the first term, and then I do minus e to the x squared. Okay. Okay. So this is the other form of the variance. This is the first one, right, that you can memorize, and this one is also good. Right. So I can also write the variance of x is just equal to this. E to the expectation of x squared minus the expectation of x quantity squared. Yeah, question. Yeah. Right. So I'm going to combine these two terms into this term. Yep. I have some quantity, e to the x squared, and I have 1 minus 2, 1 times that quantity minus 2 times that quantity. So I just get minus that quantity. All right. Yep. Good. Okay. So that's a little. Okay. Good. So this is this other form, and this. Okay. Can I cancel any more? Right? Can I say, well, one is e x squared, the other is minus e x squared? Yeah, so that's correct. You can't do it. And kind of the easiest way to really to kind of, I mean, okay, so if I could do it, the answer of the variance of any random variable would always be 0 by definition. And that would be completely useless. That would be a completely useless quantity if for any random variable that quantity was 0. Why would we be spending a whole lecture on it? Okay, so it's if I could cancel these, this would be 0. Okay, so these are different things. One is a squared term of the random variable inside the expectation. Linearity of expectation allows me to factor out linear things, but not nonlinear things. Squaring is nonlinear. So I can't factor out the squared. And the second term has that squared already factored out. Okay, so those are not the same quantity, and this difference kind of, so I can't simplify anymore. Okay, but these are equivalent. The green highlighted and the blue highlighted, these are equivalent representations. Sometimes one's easier to calculate than the other. What? They're both relatively easy to calculate most of the time. Like especially for discrete random variables, you know, it's gonna kind of be like this. The Bernoulli has 2 terms, right? But if I think probably on, yeah. So I'll do another example quickly with dice, and you'll see it's not you know, it's either way is not too hard to do. It's just writing out a bunch of terms and adding them up for discrete random variables. Sometimes for continuous ones, one turns out to be a little bit easier than the other. Try one, and if you kind of get stuck, try the other, and maybe that's easier, you know. Yeah, it can be kind of tricky. This isn't a calculus class, so I'm not going to give you an intentionally hard integral to do for work in the class, but you should kind of know how to do it if you needed to, right? Sometimes some of you will need to calculate some like variances through integrals at some point in your life. I don't know, and hopefully you could feel like you could do it if you needed to, right? It's an application of calculus once you write down the formula. And you can try both formulas, maybe one's easier, right? The one thing keep in mind is this is a constant, which you might already know. You might know the expected value already, and you can just square that. And so then that might simplify calculating the other one, as opposed to having the expectation inside. Or the, so, yeah, okay. Okay, let's see. Let's do an example with, so dice. Let's say x equals 1 to up to 6. It's the roll of a die. Okay. And so I want to know, I know ahead of time the expectation of x, I'm sure we've calculated this before, is 3.5. Okay. What's the variance of x, right? What's the variance of x? Let's go and calculate this both ways, and then you tell me which one you thought was easier. Okay. The first way is the expectation of x minus the expected value of x squared. Okay. And so this is equal to expectation of x minus 3.5 squared. Okay. And so what do? I write down the sum over I equals 1 to 6 of 1/6. That's the probability of having each of those rolls times I minus 3.5 squared. Okay, and these values, I can factor out the 1/6, and I have values here. If I put in a 1, that's 1 minus 3.5. So that's first, if I have x equals 1, that's negative 2.5 plus x equals 2, that's negative 1.5 plus negative 0.5 plus 0.5 plus 1.5 plus 2.5, right? That corresponds with x equals 3, x equals 4, x equals 5, and x equals 6, right? So those are the values that x minus the expected value of x squared can take. Oh, and I'm supposed to square, and I need to square each of these, right? Otherwise, they're going to cancel out, and I'm going to get 0, right? Those were set up. I've subtracted the mean from each of them. If you actually work that out, you will always get 0, right? The expected value of x minus the expected value, right? That's always going to be 0. Okay, but I need to square them. Okay, I forgot to square them. Good. Now I need to add these things up. And let's see, this is going to be 1/6 times, what's 2.5 squared? Oh, that's no fun. Was that 25 over 4 plus the 9 over 4 plus 1 over 4 plus 1 over 4 plus 9 over 4 plus 25 over 4, right? And this is going to be 1/6 times, let's see, is that 70 over 4? Is that right? Okay, 25 and 25 is 50, plus 18 for the 9s, plus 2. Okay. And this equals 70 over 24. Was that 35 over 12. Can I simplify? That looks okay. It's about, yeah, 60 over 4. I don't think so. I think I have it right. Those are 9s on top. Yeah, it's 3/2 squared. Yep. Good. But thanks for checking. This is 2.92 about. Okay, let's try the other way, see if it's easier. Okay. Now we're going to do the variance of x equals expected value of x squared minus expected value of x quantity squared. Okay? And remember, I knew expected value of x is equal to 3.5. Okay, so actually that second term, I kind of know already. That's already, this is equal to the expected value of x squared minus, was it going to be 49 over 4, right? That's 7 over 2 squared. Okay, so now I've kind of pre-processed this, and now I need just to calculate this term, e of x squared. This is now going to be, again, right, the sum I equals 1 up to 6 of 1/6 times I. All right, and this is 1/6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay, and this looks easier. This is 1/6 times 21. That's 7 over 2. Yeah. Ah, squared. Great. Thank you. I missed it again. Squared. That makes it a little bit harder. Okay, so that's now, what do I have? 1 plus 4 plus 9 plus 16 plus 25 plus 36. Okay, these numbers, because I didn't subtract off the mean, the expected value, are a little bit larger than before. Okay, now I need to add these guys up. Okay, I got, and this is going to be equal to 10, 20, 55 plus 36 is 91. So let's get 91. Yeah, okay, good. All right, well, I'm not quite done yet. Now I need to say, go back to this, and I say the variance of x equals 91 minus 49 over 4. And now I have to do this. Yeah. Okay, can you say a little louder? Yes. Yes, good. Thank you. Okay. This one is proving more difficult. Okay, 91 over 6. Okay, now I need to 91 over 6 minus 49 over 4. Okay, it's going to be about 2.92. Yeah, I'm gonna assume it's the same thing. All right. Hopefully you've corrected all of my mistakes. So okay. All right. So who thought the first one was easier? This one was easier. Okay. And who thought that this the one where you split them first was easier? Okay. It's about the same. Like typically it's about the same. So I thought the first one was easier personally. I made fewer mistakes on that one. So but the thing is you can always check and then you can do them both ways. A little bit extra homework for you, but if you get the same answer both times, then you know you probably got it right. Great. Okay. Okay, I said I want to say something about the geometric and exponential distribution. So let me say this for 10 minutes. Okay, okay, so the geometric distribution, okay, this is, you'd say X is a random variable for GO of P, and we described this in class of f of X for an integer K. Remember, this was a discrete one, was equal to 1 minus P times the power K minus 1 times P. Okay, that's saying if I have an event that happens with probability P, right, like I'm flipping a coin, how many times until I get the first heads? That means the first K minus 1 times were tails, right? So this is the number of events until I get the first one. Okay, so one thing I did not mention is that there is, this is with K events. There's another interpretation of this, which is basically the same thing, which is f of X of, let's use another variable, H, okay, is 1 minus P, and sometimes to the power H times P, okay? This is saying I'm going to have H, so failures until the first thing that's so positive. Okay, so, and so sometimes it's written this way. Okay, so I've just changed the meaning of H to K, right? I just say that H is equal to K minus 1. They're basically the same. H can go from 0 up to something, and K can go from, and K can go from 0 up to something too, but K minus 1 starts, can at smallest be 0, can still be 0. It's just a slightly different interpretation of it, but they're the same equation. Yeah, and they both show up. Yeah. K minus 1. It's the number of the events that failed before I got my first, well, I had K events and the first K minus 1 of them failed, right? I had to flip a coin 5 times. The 5th time was head. The first 4 times were tails. 4 is 5 minus 1. Okay, so there are a couple of reasons I wanted to bring this up. One is if you look at, Wikipedia, and if you haven't done this yet, Wikipedia is great for looking at these probability distributions. It's got these tables on the right that describe a lot of the, have plots of them, describe them, have parameters, have their PDF, or it's calling PMF here, CDF, the mean, the median, the variance, all this stuff is calculated for you, right? Right, to look it up. Probably if I wasn't thinking about this for a while, I'd probably go to Wikipedia to look this stuff up. The geometric distribution has 2 columns because both of these are somewhat common, okay? Both of these versions of it are somewhat common, so it has these 2 different versions of interpretations of it. And one has a mean of 1 over P, the other 1 minus P over P. I mean, they're similar, but they give slightly different answers. Okay, you should be aware that sometimes when you say geometric, you might mean one or the other. And in particular, why I wanted to bring this up is because in R, it uses the one that's different from the one in the textbook. And I didn't mention this before. And on one of the homeworks, they ask you to do something in R, and you may have used the wrong value because you didn't realize R had the other interpretation. So we won't count off for that on homework. That was homework 3. So we'll accept either calculation you did. We will give you full credits for that. Yeah. Yes, so it ultimately, this was the toaster question, and it ultimately depends on whether you're counting the number of successful toasts or the number of toasts you put in, including the one that got burnt, right? So that's kind of the distinction. There are these off by 1 errors. You know, ultimately in the big scheme of things for large values for large values of K, usually doesn't make a very big difference, right? For small values of P, large values of K, kind of out here in the tail, the differences aren't too big, and it kind of is modeling roughly the same thing. But if you are looking for small values of X and you have a large value of P, like in this case, I plotted for P equals 0.7, it's gonna make a really big difference, right? So sometimes you gotta pay attention to, and I would always plot it for small values to kind of check what's going on, and then you can figure out which one it's doing. Because looking at just the numbers by itself, you probably can't tell the difference. If you just calculate it without plotting, and you just looked at the value, which on the y-axis, the events out 7 or 10 steps in the future, they're gonna look pretty similar, and you probably won't notice it. Again, small difference, but you should be aware that there are these two versions of it. Yeah. That's probably the case. Yeah. Yeah, I don't know. Let me, so one thing we could do is we could say, where is, okay. We could do question. You can ask it about this. Oh, right, P and it's not saying it directly in here. Again, it might, the other one might be available. I don't know it is offhand, but yeah. Okay, yeah. So that was the other thing, and then I'm probably not going to do this lecture, but yeah. So the cumulative distribution for discrete random variables, right? You need to let's go back to here. The cumulative distribution for discrete random variables, right? F of X. This is this CDF. CDF of a value A is equal to the probability that X is less than or equal to A. For a discrete random variable, you always have less than or equal to here. It includes A. For a continuous random variable, it really doesn't matter because the probability of getting exactly A is 0, basically. Right? So if you have a completely continuous random variable, you don't need to worry about the distinction. But for discrete random variables, you can get off by 1 error if you're not careful about this. Yeah, so for discrete ones, kind of the CDF is always with the less than or equal than. But sometimes if you want, you know, right? So yeah, so you have to be careful about these things for. And the other thing I was going to talk about, which we'll do at some other time, is the exponential distribution, right? Right, is basically a continuous version of the kind of geometric. So if you think of dividing the events into smaller and smaller pieces, discretize them more and more, and it converges to the exponential distribution. And so when you get there, then that less than or equal then does not really matter. Okay, we will, I don't have time to do this today because the quiz is going to start, but I will review this probably on Tuesday. I'll probably start class by doing a review of this. All right. Okay. So the quiz will, be open now. It'll be on expectation and variance. So. Thank you. Oh, yeah. And if you want a printout of homework 4, I've got the printouts up front.